Again, this is for the lab. So the lab portion, this is the last lab. Hopefully that everybody will take care of this lab. This lab, I think, is easier than a lot of the other labs we had in before, and I think it's less work, so I'm hoping that you guys will finish it in time. And this will be the last lab for this class, so and it's going to deal with two things that we didn't really delve in them in lecture that much at all. And they are part of electronics, which are the diodes and transistors, which is the so-called nonlinear electronics, and you will see shortly why. For example, Ohm's law is not the voltage equals to a resistance times the current. Actually, the current and the voltage are have this exponential form. So that's one thing that I want everybody's attention to be focused on. So let me delve into the lab. The lab instructions and 2 Excel files are needed, and they're actually part of the upload that you have in there for the lab. There are only 4 questions, I believe, in this entire lab, so there are not too many questions. Of course, there are several tables that you need to fill, and there is already a graph there that you need to do, of course, in addition to the objective and also the conclusion. So that's basically, in a nutshell, what this lab is. There is one activity outside. There are a lot of questions that are inside in this lab in here, so I'm hoping that you guys complete everything in here beforehand, okay? I don't remember. I think the lab is due next week, so, or this weekend actually, because we want to focus on the exams after this one. So, again, these are the lab instructions: diodes and transistors. So this is a picture of several diodes. Diodes have a convention for the sign, sometimes the short leg and the long leg, or in this case, they have actually painted sides which points to where the cathode need to be, and the opposite side is the anode. Diodes are very sensitive to voltages, so you better be very careful when you're connecting them. Same thing actually also with transistors. So make sure you do them right and you don't basically damage them. Again, you need to usually leave that toward the end for the objective. Again, there is a theory in here that I'm hoping everybody will have a chance to go through and look at it and try to understand it. Like I said from before, we did the resistors, we did the capacitors, and we did the the inductors in this class. And that is really the focus of physics 4B, is the so-called analog electronics. But this is really modern electronics. Everything that is in here, if you open any device, whether your cell phone or computer or anything like that, you will find this laying everywhere in here. These things in here. You will have, usually it's near the power supply where the other things are, okay? I was looking at a design earlier, and I think I'm going to get that as part of the things I'm going to be doing with my son, and that is to build a radio basically with an antenna and all of that. So the antenna part of the radio will have an RLC circuit that is oscillating, and of course it will have a capacitor that's a variable to be tuned with different stations with different basically receptions. So that part has the physics 4B in it. Everywhere else, you're dealing with transistors and basically other components. And sometimes you will need the resistors. For example, to adjust the volume, you need the potentiometer, which is a resistor with variable resistance. So you're going to adjust it to increase the volume or decrease the volume. So there are stuff from physics 4B all over the place, but modern electronics relies a lot on this semiconductors. Again, what a semiconductor is normally, it's a very bad conductor, okay? So it's not really, it's not a conductor, it's not an insulator, but it's right in between them. But doping a semiconductor will enhance its conductivity a lot, okay? Doping meaning you add impurities to it, that's all, okay? When you do add impurities, there are 2 kinds of impurities. Those that have, if you wish, extra electrons in it. And this is the N-type doping. And those that have actually less electron, if you wish, it has affinity for the opposite direction for the electrons. So in this case, actually, you will have holes, if you wish, that's how they are called, that are missing, if you wish, electrons. That's exactly what they are. So both of them will have conduction. Both of them, they will see current, and both currents, they will be flowing in the same direction. So this is in a nutshell what this whole argument is in here. Just showing you just with a tiny addition of an impurity, like for example arsenic, in what is it, germanium that we take. Germanium and silicon are the two main semiconductors, okay? And when you do that, it increases the number of free electrons tremendously, and the material becomes 10,000 times more conducting than without the impurities. So this is a so-called N-type semiconductor. The P-type semiconductor is the other one where you, for example, add in this case different kind of doping, like gallium, for example. It has 3 valence electrons, so in this case there is one, if you wish, where you should have an electron but it's missing, so this is called the hole, okay? And the conduction in here, in this situation, you have 3 electrons that can move, and they come and replace the hole in there, in doing so as if the hole is hopping in the opposite direction, okay? So this is a so-called P-type, okay? Usually you really don't concern yourself too much with it, but you have to really be aware of which one is doing the conduction. So in this case, the electron is hopping, for the N-type semiconductor is hopping from one side to the other. And remember, the current is always opposite to where the electron is moving. So if the electron is moving from this point to the next point to the next point, that means the current is moving in the opposite direction. And here, it's actually the hole is the one that is hopping, but the hole in this case is a positive electron, if you wish. It's the same charge as the electron, but it's moving in the opposite direction. So it's a positive electron, so it's still the current is moving in the same direction. Both of them having the same, although what is doing the motion in this case is the electron. What is doing the motion in this case is the lack thereof, or the lack of an actual charge, okay? And in the same time, both of them end up with the same current in the same direction, okay? This is supposed to be a brief intro. This is not supposed to be an in-depth study into what semiconductors is and how they work. But I'm hoping to give you an overall view so that you can do at least your lab, and then maybe you'll be interested enough to continue the discussion later on. It's part of solid state physics too. So again, having this understanding that there are 2 types basically of semiconductors, the N-type and the P-type, for a diode, what it is you take an N-type on one side and a P-type on the other side. So what happened in this case, the electrons start to move and fill those gaps, at least in the immediate region where there is contact between these two, the P-type on one side and the N-type on the other side. So in that region, there is cancellation. And that cancellation, that gap, if you wish, becomes a zone that is prohibited. Now you fill it depending on the strength of the materials. So at that point, there is nothing in there. There is a gap between them. Now, if the charges come from this side, if the electrons come from this side, well, there is no problem in this case, because the electrons in this case, they will be not the currents, I'm sorry. The current coming from this side, that means the electrons are actually coming from this side, okay? They're being depleted in the opposite direction. In other words, that gap will not be a problem in this case, because you always can take electrons and replenish them from the other side. So the battery is doing the replenishing, so there is a current flowing in this direction. So the current is going to move fine in this direction. If you do it in the opposite direction, so you're piling up more electrons in here, and you're moving from the other side, so you're putting more holes. So all you're doing is increasing the gap. The current cannot travel. So in other words, what the diode is, an ideal diode, okay? It will allow current to move freely in one direction. Zero resistance, ideal one, of course. In real life, there is a finite resistance. And will prevent current, becomes basically like an open circuit when the current comes from the opposite direction. So this is not a switch that you control yourself. It's natural, the way it is, by construction, by design. So when the current comes from one direction, it's going to flow freely with unimpeded and indicated by this arrow, okay? And then when it comes from the other direction, and that's why most diodes, like this one is, they tell you exactly how you have them, how to connect them. For example, I have this diode in here. You can clearly see the legs are different in here, okay? One of them is the anode and the other one is the cathode. And you have to be careful when you're connecting them. If you flip them, they're not, the current will not work. And if you do it, and this is one convention, there is another one for the long ones that I was telling you earlier. It's connected with color coded, okay? Well, at least strip next to it. So having that in mind, so in this case, I'm connecting it to a battery. On a you need the resistor always, because if you do it this way, it's going to have tremendous current flowing. It's going to burn it. So usually for safety, you always have to have a resistor in there, okay? You really have to follow the directions when you're doing these things. Otherwise, you'll have a problem. So there will be a current in here, and that current will be more or less, I mean, it's going to be slightly off, the EMF divided by R, okay? Because technically this should be an ideal one, at least should be like a wire. In the opposite direction, it will not flow, okay? So if I take the diode and flip it around, the current is trying to be pushed this way and it's not going to go. So this current in this case is 0. But the current in here will be the EMF over R in an ideal situation. Here is a big deal in here. Here's Shockley's equation that give me how the electric field is related to the voltage. That's why I was calling it all along, and that's why it's called actually nonlinear electronics, is because the relationship between the current and the voltage is not linear, is not like, for example, in a resistor, V equal to Ri. In the capacitor, you can, in one time varying, you can also relate it to the Q and R, Q and V. Okay, are related. Even in the inductor, the rate at which the current is changing is related to the voltage. It's actually the voltage, the EMF. But in this case, the voltage is some sort of an exponential form. As a matter of fact, if you plot this function, this is how it looks like. Okay. After small voltage, very small voltage, usually typically about 0.6 volt, the current will be so much in here. So you have to be very careful, and that's why you have to have a resistor next to it in here, okay, to tame that current. Otherwise, you have a problem. So you can't, you have to be very careful with this expression in here, okay? So that's really the point of this stuff in here. So suppose that your diode has a saturation current of 1.4 microamperes, and the N, which is needed in here for this expression of 2.6, so it's given you that expression. KB is Boltzmann constant, T is the temperature, so this is dependent on the temperature, and Q here is equal to 1.610 to the negative 19. That's the charge of the electron. The voltage is the voltage that you're going to be doing in the lab, okay? So all of these numbers are given to you. You have to check your room temperature when you're doing this equation in here. You can take any app you like. If you have something that can actually measure the temperature in your room, please do that. Okay. So temperature right now, I'm looking at actually what is this one? The weather channel. I'm waiting. I'm checking on my phone. Right now, it says the temperature is 79 degrees in my place, okay? I don't know where you are right now, but you should check the temperature into where you are when you're doing this one, because we want to get a feel of it, of how much it would have been if we are in that situation. 79 degrees, I can convert it using any conversion. Actually, I gave you the expression in the bottom in here. I think it's not in this page, it's a different page. But you can convert it otherwise, just say 79 degrees in Fahrenheit. In Celsius, I'm sorry. It's 26.11, okay? Degrees, okay? 26.11. Then add to it the 273 to make sure that this is in Kelvin. So the T is in Kelvin, not in Fahrenheit. So if you plug in this expression T in Kelvin, in Fahrenheit or Celsius, you're going to get the wrong answers. So you really have to convert it to Kelvin. So if typically what you do, you convert it to Celsius, and then from there you're going to take it and add to it 273 to get the to the correct expression. I'm sorry, I'm a little bit ahead. So for this practice in here, we're going to use 295, which is slightly less than 79 degrees. Okay. And then you calculate the expression, calculate the diode current for the bias voltage I. So we're going to just plug it into the exponential, plot your results in the so let's go back into this expression, into this table. So what we have in here, we have different bias voltages, and we need to calculate the current in here for different values of delta V. So basically fill the table. And here, I'm given the current. I need to find what the bias voltage need to be so that I reach a 3 amp current. Okay? So you will see that the current starts to increase drastically as you increase the, but the current in here is in milliamps. Here it's actually 3 also milliamps. So, does everybody understand what this question is? So make sure. Oh, this last number in here is actually the maximum current that you're supposed to have, which is 3 amps as you were supposed to have in here, okay? So depending on how much current you have labeled in the diode, so this diode now here is labeled 3 amp. So how much if the maximum, what is the maximum bias voltage? So this is the question that you're supposed to have in here. So basically, everything else, use the exponential. All of these fields in here, use the exponential. You have everything in this expression. You have n 2.6, which is usually a typical number that is between 1 and 3, and which is a quality factor depending on the design of the diode itself. So that's what we're dealing a little bit with, different kind of electricity and magnetism. That's why this is a little bit different than the rest. So these laws are involve different kind of basically not a different kind, I should say a little bit more advanced topics than what we're doing right now. So we have IS. Q, it's 1.6 10 to the negative 19, N is 2.6, KB is a constant, T is the room temperature 295, and delta VD now is changing between 0 and some number in there in the table. You're going to change it. So you're going to find I. So this is easy. Use just the exponential. This is E. Do not use 10 to the power. It's E, okay, in the base E. And then at some point, we're going to assume that I is 3 amps. We have IS. We're going to we're going to move this number to the other side, I over IS plus 1, and take the natural log, and then find the delta VD. Is this question easy? Do you guys understand it or not? I know they don't have everybody in here by any search of imagination, but I'm hoping that you guys in here can see exactly what that is. Yes? Okay, at least one person agrees. Okay, so how about you for us? No? Okay, so if you guys have difficulty with this one, please let me know, okay? Anyway, so we're gonna answer the question based on the table, on what we find in here in table 1. And the question says, what is the volt? So we're going to say, what is that volt? Please use complete sentences, because I noticed when I was grading the labs that some of you would give me short answers, and that's not exactly what I'm hoping for. I hope to have the question in the rubric says full sentence, okay? So suppose that, so what is that? Plot your results. So we're going to plot it on page 7. So I need to find where page 7 is. Actually, one way of doing it is just hitting 7 in here, but you can clearly see that this is page 7. So you're going to plot it. Now, some of you don't like to do that, and they would want to go straight out and do their own in Excel. That is fine. Okay, if you're going to use it in Excel, that is fine. But remember, you have another plot also coming down on this one in here. So this is not complete. So when you do this plot, there is another graph that is going to go on this very same graph. So there are 2 functions that need to be plotted on this same graph. So this is question 1. Let me go finish this part in here. So now you may have noticed that, okay, that's that is sensitive. So this is the warning in here. Never connect diode directly to a voltage source, always diode with a resistor. And again, because of this, you will see that this thing starts to behave so wildly just with small increases, and that's because of the exponential. It's expected, okay? So so now we're gonna go back into that circuit and basically apply Kirchhoff's rule now, okay? So for Kirchhoff's rule for this one, if I have a voltage in here, that is the bias voltage on this diode, I have Ri in here, that's all. And I have the EMF. So the EMF is Ri plus the bias voltage. So that's Ohm's law. I mean, that's Kirchhoff's rule. So the voltage across the diode plus the IR is equal to the EMF. So I, in this case, is just the EMF minus delta V over DD, over R. So now in this plot, if you guys notice in this graph, where is the graph? I have the voltage in the x-axis as the independent variable, and I have the current as the dependent variable. So on this graph, we're going to graph now this different equation. So it should be a line, straight out line, depending on R. That's all. So this function now is just a function that is basically that depends on I. I mean, depends on this delta V in here. Okay. So the point being in here is we have the EMF 4 volt, that is a fixed number. R is 1 ohm. And we're going to plot this function, which should be actually a decreasing function with delta VD. As delta VD increases, this should be decreasing from 4 volt down, okay? So the current should be going down now in here, according to this function, okay? And from this point, one can calculate the voltage across delta VR. So from here, we have two functions. We have that exponential, and we have now another function that decreases from V to whatever value that we have. These two functions, they will meet at some point. These two graphs, they will meet at some point, okay? Repeat steps for epsilon equal to 5 volt and R equals to, you may check your result using an Excel spreadsheet. Okay. There is this file, which is a diode solver.xls that you have in there, okay? So you're supposed to do the plots in both graphs in there, and then you can use that Excel spreadsheet to help you with this things in here. From this one, you can calculate the voltage across the delta VR. So you can find the voltage across delta VR using these two expressions. The voltage across delta VR should be just the current I times R, basically, which is E minus delta VD. But the point being in here is where the intersect is, where the actual current is. Okay. Now, table 2, where we still have to fill it. Where is table 2 in here? Okay, we're supposed to go to this link, which I'm going to click on it. And once I click on it, we're going to have that link. And we're going to follow the instructions, basically trying to fill this table. Okay. We're going to find I. We're going to find delta VD. We're going to find delta VR, which will be just 4 volt minus this delta VD. And we're going to find delta VR, which is just I times R, which is 1 ohm. We're going to repeat the same calculation now with the E volt, 5 volt. And R equals to 5 ohms, and we're going to do the same things in here. Sorry, probably I'm, hold on, I think those tables, no, I'm sorry. Those data are related to this graphs in here, okay? This table is related to this graphs in here. So let me click on the link. And actually that question, am I still sharing this screen or not? I'm still on page 7. Okay. Let me share it again. So this is this is the second lab in here, the second portion of the lab, diode I versus V, the current versus the voltage. Again, I clicked on the link. I'm going to show you the link quickly. First, change the volt of the EMF to show 1 volt. We're going to do that. Also using any application that you know of. Enter the current value. That is the one. So the first question that I mentioned earlier used the 295 Kelvin. But now, the second question, since we're doing the actual lab, is where we're going to actually measure the temperature. So this is the one that I should have used, the 79 degree Kelvin, 79 degree Fahrenheit, and convert that 26 degrees Celsius, can add to it 273 to make it 299. So it should be 299 for me, okay? 299, yeah, 299 for me. So if I'm doing it in here, okay? Please make sure the temperature, it's always positive because it's in Kelvin. Otherwise, this expression becomes a disaster. The program works better for a temperature range between 250 and 350. So this simulation works in this range, and 299 is well within this range, okay? So if we're going to do this lab, and the lab, make sure the temperature is not too hot. I mean, if the temperature is too hot or too cold, that's going to be a disaster anyway, okay? So if the lab, because 250 is what, 20 degree below below 0 Celsius, super freezing. Okay, we're not in the lab, so we don't care about this portion. In order to connect, so do not forget. So we're going to fill table 3. So this is table 3 that we need to do now. Okay. So in this table 3, so we're going to go stop sharing that screen. We're going to change the resistance from 100, 270 ohms, 470 ohms. These are actually labeled in the actual lab. When we do it, they have this specific colors. But since we're not doing it, we're just going by the values in here, all the way to 10K ohms. Okay. And each time we're going to deal, first of all, with 3 volts. Oh, I'm sorry. This is not 3 volts. It's going to stay 1 volt. Okay. Please make this correction on this lab. This is going to be a 1 volt and then 6 volts. So we're going to change the EMF in here between 3 volt, between 1 volt and 6 volt. And we're going to find the value of delta VD and the value of I that go with it. Okay. And we'll do the same thing for the 6 volt for the EMF, change the EMF, and we find those values. Based on those, we're going to plug put the values in this Excel file. This Excel file should give me the IS and should give me also the N, the quality, the quality factor basically for this diode. Okay, so and we're going to take those numbers and put them in here. So let's get this data. Let me stop sharing that screen and share with you this screen. Okay. This is more or less the circuit I was showing you earlier. Right now, the EMF is at 1 volt. Okay, that's why I was telling you to change that EMF from 3 volts to 1 volt, because that's the only way I have in here. So I can change it to 6 volt or 3 volts. Okay. So this is Ohm's law. This is what's giving me the current. I is equal to epsilon, which is 1 volt, minus delta V, okay, minus the voltage, which is this much right now, divided by R, and R right now, we need to make it into 100 ohms. So we need to write 100 in here. And I need to put the temperature 299 because I'm doing it in here at 299. Okay? So this thing is sensitive, so please make sure you put your correct temperature, you put the correct ohms. Right now, I'm not going to read this data because it doesn't make sense at all. It's giving me an I and delta VD, so it's not exactly what I'm supposed to be. So what I'm going to do is I'm going to bring this error, and it says in the instruction within 7%. So right now it's 122%. So if I go up slightly, it brought it down to 114%. So if I go down, for example, it makes it worse. Okay. So I need to go up actually to bring it to within 7%. So right now it's 104, it's coming down. So these values are changing, and this thing, what is it doing is, it's giving me the correct, if we do it in the lab, we're going to actually get the actual value with the voltmeter. So we're going to get the actual voltmeter value, and we're going to get the current. So instead of doing that, since we cannot get the current I and we cannot get this voltage in here, we're asking this solver basically to help us find what this makes it very close from the correct value. So I need to go up further because we're still 79%. Up more, okay. I need to bring it to around less than 7%, okay. So right now it's very good actually. If I go, this was more than 7%, so this will be a little bit too much, and this one brought it less than 7%. So this is actually good. Let me see if I can make it even better. This is actually better. Okay, 1% error difference between them. It's very small. If I go back, now it's too much. So this is actually better. So what I'm going to read in here, for 100 ohms, I'm going to read 0.47 volt for the bias voltage, because the diode, and the current that is running through the resistor. Okay. So this, according to this calculations, this is, by the way, these are the diodes that I was talking about earlier. Okay. The Ohm's law give me this much current, and Shockley's expression give me this much current, and they're almost the same. I mean, within less than 1% difference between them. So this must be, if we do the actual lab at this temperature, if we are doing it at this temperature, and with this resistor of 100 ohms, this is how much we're going to get. So I'm going to report the data, 0.47 ohms, volts versus 5.2682 ohms. So I'm going to stop sharing that screen and go and share with you this screen. So according to my numbers, okay, this was, how much was it? I forgot it. This was 0.47, 0.47. And the current, it's 5.2682 milliamps. It already says it's milliamps. 5.2682. Again, this my numbers. Your numbers may be different, and they ought to be different. Okay, they should be different. Okay, so I'm going to stop sharing this screen. I'm going to go back into, if I can find where that screen was. Here. So we did 100 ohm. The next one we're supposed to be doing is go to, there are two options at this point. You can change the voltage, because you are doing the 100 ohm, so you might as well do the voltage of 6 volt, okay? So we're going to change the switch, the voltage in here to 6 volt, and the error is 165%. Or, which is still, or change this one. How much was the second resistor? It's 270. So we're going to change 270. It's probably easier. Because that's what we really should do in the lab, okay? So now the error is in 270. So if it's the error is negative, and I need to bring it up, I'm going to go down in here. So it's counterintuitive, but hopefully you guys understand in here. So it doesn't matter. So we're going to go up and down until you find an error within less than 7%. Still too much error. 2.97% is good, is acceptable. So now 0.4616, and the current is 2.024. 0.4616, where is the 0.4616, 0.462, okay? And the current is 2.0204. 2. Probably could copy, no? 02. So I have some data now. You guys understand how this works or not? You know how you're proceeding. You're going to go up and down, change the volts, make sure once you change the up and down until you get the actual value where the error is less than 7%. Keep watch on that error. If the error is increasing, that means you're going in the other direction. If the error is decreasing, and also the sign of it too. So if it could be increasing, but the negative sign, that means you're in the right direction. You're going closer to 0, okay? So as long as you get that, now you have the table filled. So I'm going to share the PDF file again. So I do all of this column up to 10,000 ohms. Then I do the same thing, but the 6 volt now. You switch batteries now, the 6 volt. So let me go into the tools in here, not the tools, comments probably. Make sure you guys catch this one, and it's actually 1 volt. Not 3 volts as it says in there, okay? You complete that, you take it to the Excel file, it's going to give you the plot, and it's also going to give you the values of IS and N. So it's actually a good thing, because both of these files have been included in the lab report, part of the instructions. Basically, what you could do also on your own, you could actually plot this function as a function of R, and you're going to find the best fit, and the best fit will give you that. So you could do it manually if you like, okay? So this is really probably the most complicated part of this lab in terms of the actual activities. And then you're going to answer this question, okay, which is related really to this, your findings in here, okay? And then we're going to get into the diodes, transistors. Transistors, basically, there are 2 types. First of all, a transistor is really an amplifier, okay? And it's defined by a gain factor. So what it is you have a base where the current comes from, and the emitter where the current is supposed to be coming from, coming out of from. So the ratio of these 2 is the so-called gain. Now, this is to make Kirchhoff's rule, the law of the nodes work, okay? So that the total current always is equal to the incoming equal to the outgoing, okay? So this is, the base is of type P, and the other 2, the collector and the emitter, of the type N. This is an NPN transistor, where this one is a PNP. So there are 2 types of transistors that you're going to find. I mean, integrated circuits, ICs, there are all kinds of connections that you might have. This is the most basic of them, okay? But again, I want you to go through the theory. I want you to read through the questions and try, because there is a saturation current in here that you're going to reach immediately, depending on this expression in here. This is basically how the current in the collector is that is needed. It's equal to beta times IB in the base, and IB and beta is the gain factor, which is typically around 100. Okay, just a number. Okay, that depends on the design of your transistor. For small currents in the base that comes into the base. For high currents that come in the base, the current in the collector is going to be a fixed number. So this is what the graph is actually. This is the current in the collector as a function of the current in the base, okay? Of course, it's a line up to a certain point, and then it's going to be the constant number, depending on 2 different values in here for R, for small r, for big R, depending on what you have in here, okay, in the circuit. This is the R we're talking about. I'm sorry. Yeah, this is, sorry, the R in the collector, okay? Again, I want you to read through this. This is a simple question that I'm hoping that you guys can read it and understand basically what the logic behind it, and plug in the numbers, because what is the minimum collector resistance? They already gave you everything. They gave you the EMF to be 10 volt, okay? And they gave you beta to be 100, and the current to be 800 milliamps. So in this case, you have IC, you have beta, which is the minimum collector resistance. So you're going to plug it into this expression. And you have IC, and you have the EMF. So you're going to plug it back, and you're going to get the expression in here. And then what is the maximum current IB? IB should be just simply, into this case, beta times whatever that value is. Again, if you have difficulty with it, please let me know, and then you draw your conclusion. This is supposed to be a theory, because at the end, because even if we had a transistor in the lab, we really don't usually mess with it. We don't even do it that much, okay? So again, the main thing of this lab is just to get this current for the transistor, for the diode working, so that you can see that dependency for Shockley's equation correct. And unfortunately, we cannot really, we couldn't, even if we are in class, we do usually build some simple stuff with this one, like for example, when the diode is on or not, okay? Of course, this is an LCD, which is actually diode too, but that's another thing, okay? So this is your lab in a nutshell, which is not really a big lab, so I'm hoping that you guys can do it and get your points quickly. I know some of you struggled in terms of the grades for the lab, and that impacted your overall lab, so I'm hoping you catch up with this thing with at least this last lab, which would be easy enough for you guys to do, without really having to get into a lot of theory, because theory of semiconductors is a very, very deep theory. It requires courses on its own. Any questions for me? Okay, very good. See you guys on Thursday. Thank you guys for coming. See you guys on Thursday. Those who are not here, this lab is important, as I mentioned, for those who are here. And please show up on Wednesday. That's going to be mainly the last lecture. We're going to talk about the, finish the lectures actually first. And then Monday, we're going to be meeting again, hopefully to go through the preparation for the exam, which is going to be on Wednesday, week from this coming Wednesday. And the final is 2 weeks from today. See you guys. Let me stop recording.